Hello everyone, myself Professor G.B. Davre. I am from Kekewag Engineering College, Nasik. Today we will try to learn second order system. So second order system is nothing but which is characterized by second order differential equation. It is having two resistances and two capacitance. Examples of second order systems are U-tube manometer, damp vibrator, two tank connected in series. So these are the basically examples of the second order system. The transfer function of the second order system can be shown by following equation: y of s upon x of s is equal to 1 by tau square s square plus 2 zeta tau s plus 1. Tau is nothing but the time constant, zeta is damping coefficient. When zeta is greater than 1, then the system is overdamped. When zeta is less than 1, then it is underdamped. And when zeta is equal to 1, then the system is critically damped. When the step change is given for the second order system, its underdamped characteristics for the underdamped second order system, the characteristics are very important parameter, and one must understand the characteristics of the underdamped second order system. This is actually the graph of the underdamped response for the second order system. The graph is plotted output versus the time. Yt is output. Some terms are there. Let me explain. T rise, as you can see, it is nothing but the rise time. Then capital T is nothing but the period of oscillation, or one can simply say period. Plus minus 5% is mentioned here. The straight line is the ultimate response time. It is the ultimate response, one can say. And B and D, C, these are the associated with the overshoot and decay ratio. So this is actually the diagrammatic representation of the characteristics of the underdamped system. So one by one we will try to learn the characteristics of the underdamped system. Starting with the overshoot, it measures how much response exceeds the ultimate value. It is a ratio of B by D. So coming back to figure, it is nothing but the how much the response exceeds the ultimate response. This is our ultimate response. But how much the response exceeds than the ultimate response, it nothing but the overshoot. Overshoot can be represented by B by D. Overshoot can be find out exponential minus pi zeta upon under root 1 by zeta square. The next property is decay ratio. It is defined as the ratio of two successive peaks. So these are the two successive peaks, C and B. The ratio of C and B are nothing but the decay ratio. Decay ratio is can be find out exponential minus 2 pi zeta under root 1 by zeta square. Rise time. It is a time required for the response to reach its ultimate value first time. So coming back to this diagram, this is a rise time. So when the response first reaches to its ultimate value, it is nothing but the rise time. So whatever the time taken by the response to reach first time of its ultimate value is nothing but the rise time. Response time, the time required for the response to come plus minus 5% of its ultimate value. So here you can see after crest and fall, the response settled down and it is coming plus minus 5% of its ultimate value. So whatever time taken by the response to come its ultimate value plus minus 5% of its ultimate value, or its ultimate value, is nothing but the response time. Period of oscillation. It is a time required to complete one cycle. So the one cycle will have the fall and the crest. So whatever time taken by the response to complete one cycle, which will include one crest and one fall, that is nothing but the period of oscillation. And period of oscillation, omega 1 can say it can find out 2 pi tau in bracket 1 by zeta square. So these are very important characteristics and we have to remember it. Next important thing is non-interacting and interacting system. This diagrammatic representation for the non-interacting system, as you can see in the figure, tank 1 and tank 2 are placed at different level. The R1 is a resistance associated with the tank 1. Capital H is the liquid level height in the tank 1. Fi is the flow rate in the tank 1. F1 is the flow rate after the resistance which is coming back to tank 2. Small h2 is the height in tank 2, r2 is the resistance associated with the tank 2, and f2 is again the outlet from the tank 2. So non-interacting system, in two tank non-interacting system, the outlet flow from tank 1 discharges into the atmosphere before entering into tank 2, and the flow through resistance depend only on height of the liquid level in tank 1. So the outlet flow rate coming from the tank 1, which will depend upon the resistance associated or height associated with the liquid in tank 1. So this flow will depend upon the height of the tank 1, is nothing but the non-interacting system. The variation in H2, that is in tank 2, does not affect by the transient response occurring in the tank 1. The transfer function of non-interacting system can be written as H2 of S, that is output, Q1 of Qi of S input, R2 in bracket tau 1 S plus 1 into tau 2 S plus 1. So tau 1 and tau 2 are nothing but the time constant associated with the tank 1 and tank 2. Interacting system, as you can see, the both tank are placed at same level. Small h is this small h is the height in tank 1, small h in tank 2 height. Fi is the flow rate which is coming to tank 1, F1 after resistance R1 which is inlet to tank 2 which is coming from tank 1. R2 is the resistance associated with the tank 2. So interacting system is basically where flow through resistance R1 depend upon the difference between height in both the tank. This is nothing but the interacting system. So this depend upon the flow which is coming from the tank 1, which depend upon the height in the both tank, which is nothing but the interacting system. The overall transfer function for interacting system is H2 of S is equal to R2 tau 1 tau 2 S square plus in bracket tau 1 tau 2 or tau 1 plus tau 2 into S plus 1 into Q1 of S. Tau 1 and tau 2 are again the time constant associated with the first and second tank. Next is controller. There are different controller: proportional controller, integral controller and derivative controller. So we will try to learn this controller. Well, for proportional controller, output signal is proportional to the error. For integral, output signal proportional to the integral error. And for derivative, the output signal is proportional to the derivative of the error. The transfer function of these controller are very important to understand. Proportional control will have Gc is equal to K. Proportional integral Kc is equal to K in bracket 1 plus 1 by tau d. Proportional derivative Gc is equal to K in bracket 1 plus tau d. Proportional integral derivative will have K in bracket 1 plus 1 by tau d plus tau d. Now this is actually the diagrammatic representation of the, one can say, the curves when we are using different controller and we are not using the controller. So what will be the effect when we are not using the controller and when we are using the different controller on the output? So control variable deviation from the initial value and time. So as you can see, one number is nothing but this is a one curve which is obtained when none means we are not using any controller. When second number of curve, that is 2, proportional controller, when we are using proportional controller, so this is the nature of the curve. Proportional integral number 3, so for 3 we are putting the proportional integral controller, and that's how this is the curve we got. Proportional integral derivative, so this 4 number curve is related to proportional integral derivative. So when we are using the P controller, as you can see, the P controller is fast, but it gives the offset. So see, second number is associated with the P controller, which has given some offset. Offset is the difference between output value and the required value or ultimate value. For proportional integral, you can see this curve is bit oscillatory, but it gives very less offset. So integral controller will introduce the oscillations, but which will reduces the offset. So eliminate the offset, but which will have the some oscillations. PID controller will eliminate the oscillation but produces little offset. PID controller, it is fast, no oscillatory and very less offset. So as you can see, for PID controller number 4, it is very less, almost no oscillatory, which is fast, has reached to response very quickly and no offset. So PID controller is more beneficial than other controller, but it is very important to know industrial application of each controller. So P controller can be used effectively to control the liquid level in the tank. PI controller can be used in vapor pressure system, temperature controlling. Undesirable offset need to be minimized, because P controller will produce offset, I will reduce this offset. So when we want to reduce the undesirable offset, then generally it is very essential to reduce the offset PI controller use. PED controller used in gas pressure control system, where offset and oscillations both does not require, and PID controller controlling the temperature and determining when composition determination is there. It is very important exact determination of the component, then PID controllers are generally used. So today we have learned the second order system is transfer function, then underdamped characteristics of underdamped second order system, controllers, interacting and non-interacting system. I hope you will understood all these concepts and you will subscribe this video and like this video. So thank you very much.